Hello, in this episode, we'll talk about the overview of neural network. This episode is largely based on my favorite book, Make Your Own Neural Network by Dr. Rashid. I shortened it and adapted the contents, but the main ideas are from that book. So here's a motivation for neural network. So which question is more difficult? I asked my nephew, who's a second grader, and asked these two questions. Can you locate the dogs in the photo? And also add these numbers. As you can imagine, second grader, it's very easy to spot here how many dogs are in this picture, but it's kind of hard for a second grader to do these things. But which one is more difficult actually depends on whom you ask. If you ask the computer will easily do this, but surprisingly, computer find it very difficult to answer the question, how many dogs are in here? Okay. So, and that's a development of the neural network is partly motivated by what we already know that the computers are good at. How can we have an algorithm that makes a computer good at also doing the task that humans are naturally good at? So what do we mean by learning? So here is a motivation. So when we say that we learn or predict, we basically have a question, and then there's a black box thingamagic that thinks and then gives an answer. In a computer, because the computers are naturally good at computing, we give a data and then let them calculate and then give an output based on the calculation. So that's sort of the basic idea of the predicting machine. So how about learning? So imagine yourself that there is a way that is kind of broken. And we want to know basically how much 100 pound, how much kilogram it is. And we try, let's say, a linear model, let's say kilogram is, and then randomly pick a number of a scaling weighting factor that we multiply to the pounds and to get the kilogram answer. So it's 100 pounds here, and then this randomly initially chose the number 0.6. So let's say 60 kilogram. Okay? So that was a random guess. What can we learn or do better? Well, we know that the correct answer here is 45.3 and the prediction is 60. So we have an error of -40. Not so great, isn't it? So then we'll take this error into account and then, well, let's try a different number, like 0.5. Now the prediction is 50. It's still a bit off from the correct answer, like -4.6. So let's try a different number, 0.4. So now we actually overdid ourselves, isn't it? The predicted output is 40 kilogram, the correct answer is 45, the error is like 5.3. It's actually gotten worse than before, isn't it? So let's just cut back our ambition and try again. Okay, so let's 0.545 conversion factor. So now we have predictive output of 45 kilogram, and the correct answer is 45.3. It's only 0.35 error. It's doing a good job, isn't it? So this is sort of like what I'm trying to say is that what do you mean by learning is that we don't know how something works exactly. We try a model, like the linear model for kilogram pound conversion with adjustable parameters. We initially guess this parameter, but then by trying out various data points, we kind of adjust them, use the error to guide ourselves how to adjust them. It's like in a radio channel in the old days, you have dial and tune into a right frequency to listen something. It's something like that, isn't it? Here's a two-dimensional example. Like imagine that I'm going to it's a Whole Foods and they have various produce and they want to basically classify them. And let's say we have banana and pumpkin. The bananas are long, the pumpkins are wide. So the length to width ratios are kind of different. We know it, and we see a banana, we know it's a banana, but can automated sensor computer can do it. So initially we start with a separating line, the length to width ratio. If this above this, let's call it banana, below it, it's a pumpkin. Well, this line is not doing a too great job. So, well, let's try another line. Let's just push it down. Well, it's not great either, isn't it? Okay. So then we keep fiddling around until we get a satisfactory answer. This seems to be a reasonable compromise. So this is sort of like we settle down to learned classification, where above this is banana, below this is pumpkin. Right? And now the prediction comes that once we have that, now any new banana that comes in, for example, we put it in here, it's an unknown produce for the computer, but given the length width ratio and it's above this line, we call it banana, and many times it will be correct then. Okay, so the classifying things is kind of like predicting things. Okay? So learning from the data. Okay, so what do you mean by use the data and learn from it? Okay, so let's suppose that in a simple world we have just 2 data points. Data 1 is likely coming from a pumpkin, and we actually know it's a pumpkin. It's a 3:1 width to length ratio. And the second data point is a banana, which is 1:3 width to length ratio. Right? So it's located here. Okay, so if we start with an initial random guess, a separating line, the slope here is here, and it happens to be 0.25 width is length. Okay, it's not so great. So we try a little bit higher line, like 0.36 times width is length, and then separating line a bit better. Maybe we could try here at 2.9 width is the length, and settle it here. So what's the process here? Well, the process here guiding the error we talked about in the first example is that, well, we have picked some slope here, times the width is actual length here, right? But then we want to go to adjust it to make it better. So in the slope, we change it. Let's say it's dA, a small amount is added. So A plus dA times width is the length. Okay? So let's here. So how much actually should we be shifting? Let's see. The error is that this is the target, this is the actual, the current prediction, this is where we want to be. So target minus actual, so A plus dA times width minus A times width. So the dA is the error, okay? Which means that we are being informed by the error. So here is an error, and the error guides us how much to change the slope. Okay? So especially here, it's an error divided by the width. Okay? So let's go through an example here. So initially we guess 0.25 times width is the length. Doesn't seem to be great because all of the produce are basically both the data points are predicted as banana. If you plug in the number here, so the actual is the width. So now here, 0.25 times, here's the data point was 3, isn't it? The data point was 3 and 1. So 0.25 times 3 is 0.75, that's the actual. But where we want to be is, this is the data point here. It's 1, but given that we want the data point to be classified when it's below the line, we push it slightly above. So it's instead of 1, we put it 1.1. So the error minus target minus actual, instead of 1.1 minus 0.75, we get 0.35. Okay. And then where we guide the change in the slope is error divided by width, 0.35 divided 3, it's 0.11. So A plus dA is 0.3667. So we got this line. Seems to be okay. How about we try the next data point? The next data point was 1.3, it's a banana. Okay. So here we have 0.36. The prediction is 0.36 times width. So in this case, the banana had a width of 1. So we predict 0.36. And the target is, so again, the banana is 1.3, but instead of 3, we want it above the line to be a banana. So we push it slightly down. So it's let's make it instead of 3, maybe it's 2.9. So 2.9 times 1 minus 0.367. So that's the target minus actual, which is the error. So it's 2.5. So given the error, the change in the slope should be, adjustment in the slope should be error divided by width. The width here for the banana is 1. We get 2.5. So it's 0.36 plus 2.5, it's kind of 2.9, so which settles us here. Seems to be okay, but one thing we notice is that once we get here, and then we see the next data point, we are swinging all the way here as if we never seen and taken care of this data point. So it only cares about the last data point, meaning the adjustment for each data point actually swings too much. The adjustment is too volatile. So can we do better? Well, here's an idea. Why don't we cut back our ambition? So when we get an error, rather than taking the full error into account for adjustment of the slope here, let's have like a learning rate to be toning down. Let's say only take half of the error and reflect it in the adjustment, isn't it? So after being informed of error, adjust the slope only by L times error of the width. Okay? What will it do? Well, let's try it again, the same exercise. So initial guess was 0.25, and the data point was at 3, so we could predict 0.75, and the error is target minus actual, and again, 1.1 instead of 1. That's the target, because we want the line to be above, slightly above that pumpkin. Minus 0.75, 0.35, and the error, the width, but this time we put an L in here, okay? Like this, okay? All right. So it's here. So we get 0.058, okay, and adjustment is 0.3 here. Okay? So it's a little bit less than before. But more importantly, when we see the next data point here, 0.383 times 1, the banana data point is 1.3. So we get a 0.30, and then the new line we target to be 2.9, so here, but the actual is 0.38 and 2.5, but we reflect only half of the error here, so we get 1.29. So adding 0.36 and 1.29, we get 1.6, which is a lot more reasonable than what we have gotten before here, isn't it? Meaning we actually took into account both the banana and pumpkin when we do the final adjustments. Okay. The key point is that moderating your learning is good. It ensures you learn from all your data and reduces the impact of outliers or noisy training data. So this is sort of motivating. First, what do we mean by learning or learning from the data? Thank you.